So example 6.3.1, normal distribution. So the length of a human pregnancy is normally distributed with a mean of 272 days and a standard deviation of 9 days. So part A, we're asked to state the individual variable, type of variable, and random variable x, and we're asked to list the givens with the correct symbols. So in this case, an individual, so we're looking at one randomly selected object, so this is going to be a randomly selected human pregnancy. And on each one of those human pregnancies, we were looking at the length of pregnancy. And they told us that that was going to be measured in days. So again, we have to keep in mind that we might have said, when asked how many days pregnant you were, you might count that and put that as a whole number, but again, it is a measurement of time, and so it is on a continuous scale. So again, this is quantitative and continuous. All right, so again, for a continuous random variable, our random variable x is going to be the measurement of a single object. And so in this case, we are going to look at the length of a randomly selected human pregnancy. All right, so now it told us to list the given information with the correct symbols. So when we are talking about distributions, these are for the entire population. So that means when they mention a mean and a standard deviation, we use the population parameter symbols for those. So for the mean, we're going to use mu, or mu sub x, and that is 272. And for sigma, or again with the random variable notation sigma sub x, that was given to be 9. And I'm just going to put it in here because it's going to be why we can use the particular functions we were, but they also told us that we had a normal distribution. So part B says to find the probability of a pregnancy lasting more than 280 days. So the first thing that we're going to need to do is we're going to need to take this English statement and transform it into a mathematical statement. So first off, we want the probability of something happening, so that's cat P in parentheses, so that reads probability of. And then we're looking at the length of a pregnancy, which is our random variable x, and we want that to be more than 280 days. Okay, so if we take that English statement and translate it into a mathematical statement, we would get cat P, so probability, parentheses, x greater than 280 parentheses. So the probability of getting x greater than 280. So now we're going to draw a picture, remembering that the center of this normal curve is 272 because that was our given mean. Okay. And we want the probability of getting x greater than 280. Now in this picture, the tick marks down here on the axis have been drawn at the 1, 2, and 3 standard deviations away. So we should recognize that where the shaded region starts here is at 280. Okay, so again, the 281 is the measurement of 1 standard deviation away from the mean, and you can see that the shaded area goes a little bit over that because it backs up all the way to 280 here. Okay, so again, this probability corresponds to this area that is shaded to the right of 280 on this picture. So to find the probability on the TI-84, looking at the picture, you can see that the lower limit is 280. And the upper limit is going to be infinity. Okay, so again, the normal distribution extends from negative infinity to infinity. Okay, even on values here, we can't have a pregnancy last negative days. Okay, but the curve itself does start out at negative infinity, and we can't have a pregnancy last infinity days either. That would be insane. Okay, 9 months is long enough. But again, the curve that we use to model that situation does extend out to infinity. There's basically zero area out there as we're computing these. All right, so the calculator doesn't have infinity on it, so we're going to use 10 to the 99th power as a close enough approximation in stats. So again, if you're ever in a calc class and you're doing limits as x goes to infinity, you do not plug in 10 to the 99th power. This is just close enough approximation as we're looking at a stats class. All right, so now you should take out your calculator, and as we're going through the videos, you should be making the key punches and make sure that you are seeing view screens that match the view screens that are here in the textbook. So in this case, we want the probability that x is greater than 280. So we said our lower limit here is 280. The upper limit was infinity, so we would have entered a 10 to the 99. So in here again, we would have hit second vars to get into the distribution menu, and we would push button 2 to get to normal CDF. Okay, so lower endpoint is 280, the upper is 10 to the 99th power, and then we enter 272 is our mean, and the 9 is our standard deviation. Okay, and then we push enter, and so we get this 0.18703. So that is the area of the shaded region in the picture above. Now again, we're not going to be using StackCrunch in this unit, but if it's open on your computer and you want to type some things in, we just notice it does give us the exact same answer that we got here on the calculator. So putting these together, we have the probability that x is greater than 280 is going to be equal to this normal CDF, 280, 10 to the 99th power, 272, 9, which if we round that off is about 0.187, or if we wrote it as a percentage, 18.7%. So again, this one I will interpret two ways, but again, on some future ones we'll interpret it one way, realizing there's always two ways to interpret these. So again, we can interpret this percentage for an individual or as a percentage of all. So we could say that there is about an 18.7% chance that a randomly selected human pregnancy lasts longer than 280 days. Or we could say about 18% of all human pregnancies last longer than 280 days. Okay, so again, every probability we can either interpret for an individual or a percentage of all. And again, just depending on the context and the question that maybe we have been asked, we would prefer one over the other, but again, both of them are legitimate interpretations.